Good morning, everyone. We are into the 6th lecture on this course on applied electromagnetics. Today we are going to learn about, in fact, we are going to review some of the concepts we already know, and we will augment the knowledge with in relevance to orthogonal coordinate system that we learned and bringing in vector calculus into play for the course. So the first thing that we are going to have is a brief introduction on the calculus, and then followed by we'll talk about the differential line elements, surface area elements, and volume elements that we will be employing frequently throughout this course. Okay, and then we'll nail the concepts that we are going to learn in this class with the two problems which I call it as signature problems for you to understand what this differential element mean, okay, or the infinitesimal elements mean. So here is a charge that you see here, and this charge, let it be positive q, and from where we are having the field lines, electric field lines that are diverging out. So always remember that from positive q there is always field lines that are emerging out, and from these field lines what we want to know is I want to know what is the electric field, okay, due to this plus q in space. Then it is easier when we employ the spherical polar coordinate system to estimate the electric field, and we can do it fundamentally using the principles of Coulomb's law, or we can also do it with what is known as the by constructing an imagine Gaussian surface and then apply Gauss law to estimate the field in space. Okay, in employing Gauss law to estimate the field in space, we will be requiring to know what is the differential element in the for the corresponding surface that we are going to take. Okay, in this case it is a spherical surface, therefore we need to know what is the spherical surface, and you can see that the field lines emerge out of a positive charge from here, that you can see that it is isotropic in nature, it is radially symmetric. Okay, so it is all outward, it is flowing outward from a positive charge along the radial direction, and I can construct a imaginary Gaussian surface, and at any point on this Gaussian surface, suppose if I want here, then what I need to do is I need to construct an imaginary Gaussian surface around here, and we require to know the surface area element in spherical polar coordinate system. Okay, that is what we are going to learn today in today's class. Similarly, another example is, let us say I am actually having a solid cylinder, and in this solid cylinder it is uniformly charged. So I can actually, this solid cylinder that you see here is uniformly charged, and I am going to define this charge density that is present in the volume of the cylinder as rho. So volume charge density is rho. Okay, see this rho is different from the rho which you use it as a cylindrical coordinate system. Okay, so whenever I use rho, I will be very specific in defining that rho to be either the cylindrical coordinate or rho to be the volume charge density that you see here. This construct, if I want to know how much charge, total charge is there inside this cylinder, then I need to get the volume integral evaluated, and the volume integral is, in this case, will be rho d tau. So the rho d tau can be evaluated based on this to estimate the total charge present in this charged cylinder. Another example that I would like to give is the magnetic field calculation, and for magnetic field we know that the current carrying wire that you see here, in this direction it carries the current, this is a wire, the line that is shown here, and this, it carries the current here. The current carrying wire produces a magnetic field surrounding this wire using this right hand thumb rule. Okay, so this is what you are seeing here, and so it circles around the wire like this. Now I want to know what is the field at any point in space surrounding this wire. Then actually I can employ the Biot-Savart law and use vectorial concepts, okay, and estimate the field at any point over here on this ring, like here or here, anywhere I can check it and integrate over the this line. So here we will be talking about, we can do that way by taking the basic concepts over here, and then alternatively what I can do is I will be also, so here I will be using line integral concept, but alternatively if I construct a what is known as imaginary Amperian loop, and in this case the wire possesses a cylindrical symmetry, I can use the cylindrical symmetry to nail this problem also. Okay, so there are two methods. In all of these cases, what I want to show is we need to know what is the differential line element or surface area element or volume element depending on the problem that we are going to face. So these are the three things that we need to know. I will say line element, surface area element and volume element, and these differential elements are also can be called as the infinitesimal line element, infinitesimal surface area element, infinitesimal volume element. So I have given you a brief introduction. Why do I need to study this topic, differential, line element, area, surface area element and volume element in relevance to the course that we are undertaking in this subject. Okay. So this is the imaginary Amperian loop. Now, having said this, let us take a step backward and look at the introduction. What is the fundamental difference between the ordinary calculus that we know we have been learning from high school to the vector calculus? You have been introduced to the vector calculus concept through rectangular coordinate system in the previous semester. However, I would like to little bit discuss about that aspect. Now let us say I have a function in xy plane, and this is a gradually varying function like a sinusoidal wave. Okay, and this function f of x varies with respect to x. Similarly, there is another function here. Again, it varies with one variable x in this fashion. The difference between these functions which are shown in the left hand side and the right hand side of the screen is one of them is gradually varying, the other is the rapidly varying function. Now, how do I describe this variation with respect to the variable x is what we bring in the concept of differentiation. If I differentiate this function f of x with respect to x, I will get the slope of, geometrically I will get the meaning as the slope of this function. We can tell what does this slope imply. The slope implies that how much this function vary when I vary the variable by a small amount. Okay, so that is the idea. But you can see in both these functions, the slope does not change linearly. Slope is not constant. Okay, slope actually varies depending on the point where you are. It varies. Here the slope is 1, and here it is going parallel to the top of this one is going parallel to the x-axis. There is no, the slope is 0 because dy by dx, okay, it is parallel to this, so you will not have any slope. Okay, and dy is 0 and dx is changing. 0 by anything will be, so angle will be, slope will be 0, and here again slope will be 0. There is a decrease in slope, there is an increasing slope, so it goes like that. In this case, you can see over here the slope increases rapidly, which means even for a very small increase in x, the f of x increases rapidly. In this case here, it varies little gradually as compared to over here. So this is what the idea of derivative, and when you integrate this derivative within the limits with the variable, you will get the function back. So in essence, integration and differentiation are inverse process or reversible process. You can get the function back. Okay. Now, if the function instead of varying with one variable, let us say if it varies with 3 variables, then the problem is little tedious, not undoable, but you can do it, okay, by invoking partial derivatives. Now, in both these cases, whether it varies with 1 variable or 3 variables, if the function is a scalar function, then we can employ these differentiation concepts and get the derivatives. What if the function not only varies spatially along 3 coordinates, but also it varies with respect to direction? For example, if I am in a room and the temperature I am reaching from one point to another point, it's a very pretty large room. Depending on the direction of the how I move, the temperature is going to vary differently, in which case the derivatives, when we have to construct, it could be n number of derivatives. That is what in principle it looks like. However, the problem is not as complex as we think. Okay, this answer to this question, whenever we go about with respect to having the temperature variation spatially, and if it varies with the direction of my movement, then how am I going to go about it? This question I will discuss in detail when I introduce the concept of del operator. For now, this is one thing. Here is where we need to employ vector calculus into play. We will come to that in the next class. Having said that, now come to, I want to introduce this concept, the line element. Line element, where is it used? Okay, so that is the first thing. What is the line element or what is the infinitesimal line element in rectangular coordinate system to begin with? What is the to describe that, I am going to show you a picture. Here you see that it's a Cartesian coordinate system that you are seeing along AX, AY, AZ direction, and this cube that you see here is the infinitesimal volume element, and if I want to go from one point to another point, I can take very small steps along AX direction and finish that along AX direction totally, and then I can take very small steps along AY direction, and then I can also move along Z direction by taking very small steps. These small steps are what are known as infinitesimal elements. Okay, so how do I represent mathematically? Here is how it is done. Mathematical representation for this line element is going to be dx, dy, dz. Okay, where do I use this? So here you see that there is a charge over here. Again, I am bringing that concept and of field lines that is emanating from a positive charge. And suppose I want to bring this another. So what I call the capital Q as the source charge, I bring the test charge. When I bring this test charge in space, I have to do work and against this field and place this charge over here. So how much work needs to be done here is evaluated by what is known as the, you know that well-known formula, work done is nothing but the small q into the potential at this point, potential due to the field lines of the positive charge. So I have to work. To do the work, how much? So that is the energy that I will be storing in the charge to put it here. So I will be doing work to bring this charge and place it here. So to calculate this, I will be employing the line integral. If I know the force function, I can employ the line integral and I can calculate it as integral f dot dl with the suitable line integral limits. Okay, so that is how it is done. Therefore, what is this dl? dl is nothing but the small steps along the x direction dx plus small steps along y direction dy, small steps along z direction dc. So in principle, it does not matter how I walk, the addition is always commutative, the direction independent, which means I can walk along z direction to begin with and then walk along y direction, and then I can walk along x direction, or first I can walk along y direction, then I can walk along z direction. Okay, so it doesn't matter as long as I reach the point anywhere in space, the point that I desire to reach. So the importance of line element can be understood when we calculate the energy stored in an electric field or the work done in bringing a test charge and placing the test charge in space against a source field, and this is what exemplified in this diagram. Now, going further one step, I told you if I want to calculate the flux due to the field flux that you saw these lines, this field emerges out of the positive charges, and whereas on a negative charge it always closes in. Okay, so it comes towards the field lines, comes towards the charge, whereas from positive charge it diverges out. So these field lines, where they flow out of the surfaces, and if I want to calculate the flux that is flowing out of the surface, I will have to integrate, I will have to bring in the concept of surface integral, which is a double integral, and I need to take the appropriate surface area element into play. So I will construct, so here I show a cube which is superimposed on a XYZ coordinate system, and let us say I assume that there is a charge which is placed inside this cube, and the field lines are, and let it be a positive charge inside this cube, the field lines are flowing all around this cube, and it is emerging out of this cube because it's a positive test charge. And these field lines, if I want to evaluate with respect to this space, I will have to take this area into play. If I have to talk the flux that is flowing out of this plane, so how do I visualize this plane? We know in Cartesian coordinate system, where x is constant for the front face, we call it as x plane. Okay, so depending on here, let us say it's a unit cube, then this becomes 1, this becomes 1, this becomes 1. So I call this plane as x equal to 1 plane, y equal to 1 plane, and z equal to 1 plane. Okay, so to take this appropriate surface area element, I am going to take, for example, let us talk about x equal to 1 plane, which is the front plane. The appropriate surface area element is going to be this one. When I integrated all around this with the proper units of x and y, I am going to get the total flux that is flowing out of this entire surface. So this infinitesimal surface area element that you see here is shown in the shaded area, and you can see that it is actually dz along the infinitesimal line element along the z direction multiplied by the, so length into breadth. But only thing is, this area that you are seeing is an infinitesimal area element. Infinitesimal means it is small, and this, because the flux is flowing out of the from a positive charge, there is a direction associated with the flow of the flux. We will again stress this aspect. How do I do this when we talk about divergence? Okay, so this flux is flowing out of the positive charge, and I integrate with the suitable limits along the y and z direction. I will get the so this is double integral. So I will have to perform double integral, and then similarly for this phase it is y equal to 1, which means x and z are varying for this plane, and therefore I will have to take appropriate surface area element. Again, for the top surface I have to take z equal to 1, which means z is constant, and there is a direction associated with the flux movement. So I have to employ the right, there is a direction obviously associated with the surface area, and outward normal is always taken as positive directions. So that is what is exemplified or illustrated in this figure. Okay, so the direction of the unit vectors are shown, and it is along the positive ax direction. In this case, positive y-axis along this direction, positive z-axis along this direction. Okay, here is what. So what are the surface area elements magnitude wise? Magnitude wise, for this plane it is going to be dy dc. For this plane it is going to be dx dc, and the direction is ay. For this plane it is dx dy az. Okay, so with the suitable limits, when we integrate, we get the total flux flowing out of the surface completely. Okay, so that is the good approach. You can, integration is nothing but, instead of doing repeated additions, what we do is when we integrate suitably, we can get the total flux. This, you know this concept very well. Okay, and then here are the planes which are shown illustrated beautifully in this figure. what are constant. So whenever we talk about surface area element, we need to know what is the plane. How do we define the plane? So we call it as x equal to constant is x plane, y equal to constant is y plane, and z equal to constant is z plane, which means it is actually x. When x is constant, it is yz plane. When y is constant, it is zx plane, and when, because it's parallel to zx. Okay, so that is what it means. Okay, so similarly, when z is constant, it is parallel to xy plane. Therefore, alternatively, you can also tell by map it with respect to the coordinate. It is which is constant. Okay, z equal to 1, z equal to 2, which means it is an xy plane parallel to xy, and it is at equal to 2. Now come to in cylindrical coordinate system. How do I define this line element? So again, I draw this illustration in in the entire course. There is a need to develop this imagination aspect. Moment you can imagine things, you can easily retrieve the concept without having to sweat and memorize. The more you how much can you memorize in any case. Okay, so it is important to understand the concept and run with it. So having said this, we know that in cylindrical coordinate system there is 2 linear parameters and 1 angular parameter. So in linear parameter we know how to work. So what are the 3 coordinates in cylindrical coordinate system? It is along the radial direction rho coordinate, along the z direction it is z coordinate, and then there is the azimuthal plane. We walk in the angular moment. But so to get this differential line element or infinitesimal line element in cylindrical coordinate system, first of all I want to write what is there in Cartesian coordinate system and then go from there. So the one thing that you must realize here is dx, 2 linear, all the in Cartesian coordinate system all the parameters are linear, therefore you can write like this dx, dy, dz. But in cylindrical coordinate system we are encountering one curved surface, correspondingly we get that is a cylindrical surface, correspondingly we get one angle, and we know the relationship angle equal to arc by radius. So the arc is along the infinitesimal moment along the this direction. So therefore in the curved direction, and therefore we can write dx, let us say it is along the radial direction, so we can write it as d rho a rho along the radial direction plus rho d phi. Okay, so that is what is exemplified in this formula here, and here you can see that along the z direction, z and is the same both in Cartesian coordinate system and cylindrical coordinate system. Therefore I am just rewriting. So I just wanted you to show the similarity between the cylindrical coordinate system and the cylindrical coordinate system over here and the Cartesian coordinate system over here. So showing this relationship, what I want you to realize, whenever we take infinitesimal line element moment, we can imagine that to be linear. So because angle equal to arc by radius, I can you know this formula and you can get that. Okay. Now what is the so we have already seen what is the surface line elements. Now we can go to surface area element, which is shown here. So along a rho direction, when the plane is perpendicular to when the surface is perpendicular to a rho, it is going to be the magnitude of that surface is infinitesimal surface area element is going to be rho d phi dc. When the surface is perpendicular to normal to a phi direction, the surface area element is going to be dc d rho. When the surface is perpendicular to ac direction, the surface area element is going to be d rho d phi. Okay, or rho d phi. Okay, and we take this surface area element, infinitesimal surface area element, and integrate with suitable elements with respect to the function that we want to carry out. Okay, so here we talk about what is known as the double integral or surface integral. Okay, so it could be a in some cases we might more often we will be dealing with closed surfaces, but we can also do with open surface. Okay, so these the 3 directions the surface area elements is shown, and these are the magnitudes which are mentioned over here. And how do I again visualize the three constant planes which I talked about in a rectangular coordinate system. Similarly, I can have rho plane, z plane, and phi plane, which are shown with this shaded. So here, when I take the circular cross section, and it is actually the z is constant, and then I will get this plane. Okay, this plane z constant. Now, if I go along the radial direction of the cylinder, the radius is constant. Therefore, when radius is constant, then I will have to take this surface area element in integration. When z is constant, I will have to take this plane, which is rho d phi, as the surface area element and integrate with suitable limits of for rho and phi. When I take phi as constant, the phi plane, which is shown by this rectangular plane, here the phi is constant. For this rectangular, phi is constant. When phi is constant, I will have to take the suitable limits for the z and the rho, which means z can also vary like this, and rho can also vary from 0 to the rho value, which could be anything given in the problem. Okay, when we do these problems, you will get little more, but for now you can understand what is constant, what is to be. So to remember this, whenever some variable is constant, that is the plane we are talking about, that will be the direction. Okay, so when z is constant, the direction of this normal to the plane will be az. When phi is constant, the direction of this plane is going to be a phi. When rho is constant, the direction of this plane is going to be a rho. So you can see the normal directions which are shown here. Now come to the spherical polar coordinate system. How do I write it? Again, visualization is very important. So here is how it is done. So the infinitesimal element is shown in this shaded region by blue color, and you can see that in spherical polar coordinate system we have two angular parameters, one linear parameter. Therefore, we are going to take two angular parameter. What are the two angular parameters? We know it is phi and theta. So we have to have the arc properly done. Okay, arc length properly done. The only thing is, when we talk in case of cylindrical coordinate system, whatever the radius vector remains the same in the xy plane. Whereas when we talk about the spherical polar coordinate system, which means we take the spherical symmetry into account, here the radius vector have to be projected onto the xy plane. So the projected vector comes in play. So here is how it is done. And again, I bring up the concept of writing the first the infinitesimal line element in Cartesian coordinate system as dx ax hat plus dy ay hat plus dz az hat, where dx dy dz are the infinitesimal line elements along x, y, z direction respectively in Cartesian coordinate system. And here all the three are linear parameters. Therefore, when I want to take two angular parameters, I need to take the corresponding arc length. We know the coordinates in spherical polar coordinate system is r, theta, and phi. So the radial vector, when it is projected on azimuthal plane, the projected vector is going to be r sin theta. Therefore, we have to take that into account when we talk in terms of this. So the corresponding infinitesimal line element can be gotten by using this simple formula, angle equal to arc length by radius. For when we make a small movement in the angular direction, we can actually, when it is a small movement, very small step, like a newly born baby, say around 6 months or something, when it takes the small steps moving from one coordinate to another coordinate in our homes that we have seen, it takes very infinitesimally small element. Okay, so we can see that movement, and that movement is more often, you can remember it, that it is a you can approximate it to the linear approximation, and from there we can get angle equal to arc length by radius. To get that arc length, correspondingly we use this. So in along the radial direction, d theta is nothing but arc length along the radial direction divided by radius, which is r. So we get arc length equal to r d theta. In case of the phi plane, the projected vector is r sin theta. Therefore, we are going to get the arc length in the phi direction as r sin theta d phi along a phi direction. So this is how the infinitesimal line element is written, and this is in the spherical polar coordinate system. You don't have to memorize. If you understand the simple concept how infinitesimal line element comes, then it is very simple, and all we do again and again is the angle equal to arc length by radius. So corresponding three coordinates, you have to write it like this. And if it is a projected vector, first you have to take the projection into consideration, and then use this infinitesimal angle that you make. So here I make an infinitesimal angular moment of d theta. Here I make an infinitesimal angular moment along the a phi direction as d phi. So depending on the arc length over here, you take that corresponding projected vector over here, and here it is the radius. So you can see that for dy, I have taken r d theta a theta along the a theta direction, and r sin theta d phi along the phi direction respectively. So the three coordinates r, theta and phi. So the corresponding directions are ar, a theta and a phi, and the corresponding arc lengths are in this case it's a linear parameter. So straight away dx can be construed as dr. That is the infinitesimal radial along radial direction that I am making moment, and in the case of theta it is going to be r theta. In the case of phi it is going to be the projected vector that comes into play, that is going to be r sin theta multiplied by the infinitesimal angular moment d phi. So this is how we get it. Now if I want to take the surface area element to evaluate the surface area integrals, we have to take this. This is how it is done. Again, we can have a flux emanating out of the positive charge, and imagine this one Gaussian surface, and evaluate what is the field due to this source charge at any point by bringing in to play the spherical polar coordinate system. We will have to use Gauss law, and Gauss law, as you will see, is the closed surface area integral E dot ds equal to q by epsilon naught. So we will be knowing that. Okay. So how did we get this ds value for surface area is what we are going to see here. And then once I know the appropriate surface area element, I can easily integrate that. Okay. There is a typical method, because when electric field and ds points along the same direction, we know that when two vectors are pointing in the same direction, the dot product is nothing but the cos of the angle between the dot product will be 1, because the angle itself is 0. Therefore, cos 0 is 1. Therefore, you can take the E will be constant, and in such a case, and ds, this integral, double integral ds, so it will be the total surface. So we can easily evaluate by Gauss law when we take the appropriate surface area element employing the suitable coordinate system, as we will be seeing when we study about Gauss law. Right now, the purpose of learning this double integral, triple integral and line integral, that is what I am trying to make. So to emphasize, I am bringing in the concept of the electrostatic field or magnetic field, just to give you a feel why we are learning this subject. That's all my point is. So the corresponding surface area element in spherical polar coordinate system is shown in this diagram illustration, and we can see that when along the radial direction, it is the other two parameters that which means r sin theta d phi, and you multiply with the same thing. It is like because these areas, the surface areas that we are talking about, although it is shown in the diagram as big, it is really extremely very small. Therefore, you can consider it to be a linear approximation. So you multiply length into breadth, you get r square sin theta d phi ar direction as this surface area element for this. In this case, it will be r sin theta dr d phi along a theta direction. In this case, it will be r theta dr along a phi direction. So you remember these diagrams show the surface area element, but for illustration purpose, these surface area elements have been shown as drawn as big, but in principle they are going to be extremely small. Therefore, we can do the linear approximation to calculate the length into breadth and get the directions. The directions or the directions of these three planes will be what will be the parameter that will be constant. Along when I talk about R plane, the R is constant. Therefore, the outward normal will be AR. When I talk about the theta as constant, which will be the theta plane, then the direction of this plane will be along A theta. When I talk phi as constant, the plane will be the phi plane and phi will be constant. Therefore, it's a phi plane and the corresponding the other two parameters come into play. Okay, so the differential the magnitude of these three planes are written over here for your this thing. And remember, surface area in electrostatics we will always associate with the directions because there is a specific direction in which the flux flows. Okay, due to a charge or a current configuration. When it is a charge, it is going to be electric flux. When it is going to be a current, it is going to be magnetic flux. And we will be using the surface area element, but remember you have to associate the direction because there is a particular direction in which these flux lines flow. I am re-emphasizing this concept time and again because you may not have encountered that there is a direction associated with surface. In the context of flux movement, there is a direction. Therefore, we bring in the concept of direction, and for consistency, we always say that because from positive charge, we always have the field lines diverges out. Okay, so it is like diverging out, whereas when it is coming, okay, together, okay, when it is flowing into the charge, it will be a negative charge where it is all sinking in, therefore it is converging. When it is a case of negative charge, the field lines converge. When it is a case of positive charge, the field lines diverge. Okay, so remember that aspect, and we have to take appropriate direction to get this flux flow. Okay, so that is very, very important. So here is the other diagram which shows which plane. If I take the plane on the spherical surface, R will be constant. If I take this plane, when I have here theta is constant. How do I get theta constant? Theta, you remember, is the angle that the radial vector makes. Okay, so if I draw a radial vector from this origin, okay, so here is the origin to this coordinate system. When I draw a radial vector, and this radial vector makes an angle theta with the z-axis. If I rotate this radial vector around this z, I will sweep a cone which is shown as theta constant. Okay, I want you to imagine when keeping theta constant, you rotate the radial vector like this, you get a cone. See my hand, you can see that. And similarly, you can have the phi constant because the angle phi is the azimuthal angle, and in this plane, the rectangular plane that is shown here, phi is constant. So the corresponding direction for the surface area element is going to be r d theta, and direction is going to be a phi, and the magnitude is going to be r d theta and dr. You integrate over suitable limits corresponding to the surface that we are going to consider. Now let me exemplify this usefulness of this surface area elements and volume element by these two typical problems. Calculate the curved surface area of a cylinder of radius r using the double integral method, assuming an infinitesimal surface area element in the appropriate direction. How do we go about it? Okay, so first thing, when such a problem is given, again you bring the illustration into play and the illustration comes back. So this is 1 octant of a cylinder that is shown, and this is the infinitesimal surface area element, and here we are going to get the curved surface of this cylinder, which means what is the direction that is going to be taken into play. So here when we talk about the surface area, we are going to have as r d phi dc because the radius remains constant, whereas the phi is changing, it is changing. I need the surface area of the cylinder. So here is my cylinder. Okay, let us say you see this, I want to know this cylinder. If I want to know the cylindrical surface area, what I am going to do is, you can see that the phi is changing and also the z is changing, whereas the radius remains constant. Therefore, the surface area element for the infinitesimal element is going to be along the radial direction. Therefore, the other two parameters you have to multiply. That will be r d phi dc. Because the radius is constant, I took the radius, given radius as capital R here, and that will be out of the integral because the radius is constant. I have to integrate this d phi and dc variables with the suitable parameters. Here is how it is done. I show it, the height of the cylinder being h. So I have to integrate all from 0 to z for h for the z variable, and for the phi, we know that the azimuthal angle takes the limit from 0 to 2 pi. I integrate, I will get 2 pi r h, which is not unexpected, which we know very well. So therefore, you can see the usefulness of the here. What I have done is, when I integrated, because I am only asking for the curved surface area, which means I am only taking the magnitude. Therefore, however, I need to understand what is the, because there are three surfaces as we discussed for any three-dimensional objects. It could be radius constant, r plane, and which will be rho plane in this case, then phi plane, and then z plane. So depending on which is constant, because we are talking about curved surface area, I can also ask you to calculate the surface area of this cross section of a cylinder, which is a circle. And in this case, I will have to, when I want to calculate the, for example, this is my cylinder. I want to calculate this, the top surface. Okay, I want to calculate. In this case, the radius is changing, phi is changing, but the height remains constant. So I have to take corresponding direction to get this surface area. But here, since we are not involving, only we are calculating the magnitude of surface area, we are only taking the magnitude of that corresponding surface area element into play. But when we want to do with vectors, okay, vector calculus, we need to take appropriate dot product or cross product depending on the physical parameter we want to estimate. So do not worry about it. We'll come to that throughout this course. But we need to bring this surface area, appropriate surface area element into play there. All I want you to understand here, when you evaluate a surface area integral, you need to take the symmetry into account, and after symmetry, you also look into account which plane I am talking about. Okay, what is the constant parameter? Accordingly, you must take the other two parameters which are varying. Okay, similarly, if I say, for example, if I take a xy plane, okay, xy plane means a plane which is parallel to xy, and z will be constant. So my surface area element in Cartesian coordinate system for the infinitesimal area is going to be dx dy with along the z direction if it is an xy plane. So if it is x plane, which means x is constant, the other two variables are y and z. So the corresponding infinitesimal area element is going to be dy dz along the ax direction. So think these two concepts if you are able to, and then you have to remember the direction of the surface area element, because when you take dot product, you can take dot product only between two vectors. Okay. Similarly, when you take cross product, you can take cross product only between two vectors. Okay. We will be employing this dot product, cross product. We will be looking into the directions. We will be employing this symmetry, and we will bring that symmetry into play and choose the appropriate coordinate system to nail the problem. Okay. So there is another example that I want you to show the usefulness of the wall. Calculate the volume of a solid sphere of radius r using triple integral method. We know that volume means we are bringing the three coordinates into play, and here it is a spherical symmetry because I have asked you to calculate the volume of a solid sphere of radius r. So we know that along the infinitesimal line element along the r direction will be dr, along the theta direction it will be r d theta, and along the phi direction it is the projected radial vector on xy plane which will be r sin theta d phi. So when you multiply, you get this infinitesimal surface area element. By multiplying, you get, actually I got to multiply dr into r d theta into r sin theta d phi. When I multiply, this is my volume of an infinitesimal element along. Okay, so here is there is a small typo over here. I will correct. So infinitesimal, there is no direction for volume. So this is it. Okay. So volume of an infinitesimal element is r square sin theta dr d theta d phi, and once I have that, I will have the volume evaluated with suitable limits as shown, which I have not introduced in case of the spherical polar coordinate system. Remember, when I want you to imagine, okay, a sphere, if I want you to calculate the entire volume of the sphere, the phi can vary, which you know very well. The phi is the same coordinate both in cylindrical coordinate system and the spherical polar coordinate system. Therefore, phi varies from 0 to 2 pi. It takes the entire circle, which is not difficult to imagine. The theta is not varying from 0 to 2 pi. Theta varies only from 0 to pi. Okay. Why? Because if I take 0 to 2 pi, and if I also do this 0 to 2 pi for the phi, I will be taking every point twice into account, okay, in space. Therefore, you will not get the right answer when you take 2 pi. You will have to only. So if I want to reach any point on sphere, it is enough to traverse 0 to pi along the theta direction. It is not 0 to 2 pi and again 0 to 2 pi here. If I do that, I will be evaluating twice. Okay, so please try to think, give a pause and think. The theta varies only from 0 to pi. This is the main point on this. Okay, for the limits, whenever you take in the polar angle varies only from 0 to pi. It is not varying again like this. Okay, it is not 0 to 2 pi. I emphasize this point very carefully because this is something that we will be using throughout this course. So it varies only from 0 to pi. The reason, because if I take 0 to 2 pi for theta as well as 0 to 2 pi for phi, then I am going to evaluate the integral twice, which is not correct. Therefore, when you estimate, I will get this volume as 4 by 3 pi r cube, which is again not unexpected. Therefore, the usefulness of infinitesimal volume element. What integration means is repeated addition. Okay. The only thing is, if I have n number of elements, to add n number of elements is cumbersome. Integration with suitable limits we can get in one go. So that is the usefulness of integration. Integration means bringing together, adding it together. Differentiation means separating. Okay, so keep that aspect in mind. I am sure that you know this concept right from high school. Thank you. We will take up some problem on this line integral, surface area integral and volume integral at an appropriate time after discussing about gradient. Then we talk about when we talk about gradient theorem, we will be encountering line integral. When we talk about divergence theorem, we will be encountering surface area integral and volume integral. When we talk about the curl theorem, we will again encounter line integral and surface area integral. The corresponding elements have to come into play, corresponding symmetry have to be imagined, and those elements have to be taken into consideration. So keep these aspects in mind. So this class is important from that perspective. Thank you so much. We'll see you in the next class. Thanks.